Functions, page 14, number 2. For each of the following functions f, find the inverse function, and then sketch the original function and the inverse function and the diagonal line y equals x on the same set of axes. Then show that the inverse function following the original function is equal to the original function following the inverse function equals the x. In other words, the identity function. So show that both of these functions following their inverses or vice versa are going to go back to the original input, which is x. Okay? And maybe you don't know what that means, but let me just go through this problem and then you'll understand. Okay, so first thing is we want to find the inverse function. And the easiest way to find the inverse function is to write it out as y equals 2x plus 5 and then do variable interchange. So we'll do variable interchange here. And the first step is to interchange y and x. And then we solve for y. So we're going to subtract 5 from both sides. We're going to get x minus 5 equals 2y. We divide both sides by 2, and we get y equals x minus 5 divided by 2. Okay? And then we're supposed to show that if we do inverse function following the original function, we're going to get x back. So let's try that. So we'll say, okay, we're going to start out with the original function first, so that would be 2x plus 5. And we're going to put that inside the x for the inverse function. So we put 2x plus 5, we put that inside the x right there. And that gives us 2x plus 5 minus 5 divided by 2. If we subtract 5 from 2x plus 5, we get 2x divided by 2, and 2x divided by 2 is equal to x. Okay, so we can see that basically we got the original input back. So indeed, inverse function following function is equal to the original input. And then let's test out the opposite. The opposite would be the blue function, which would be x minus 5 divided by 2 inside 2x plus 5. And then this would give us x minus 5 plus 5, which is equal to x. So it gave us the original input back again. So we have done these tests, and we've shown this, and we've shown this, both equal to x, the identity function. Okay? So the identity function just means that if you have a function like this, the input is equal to the output. That is the identity function. But the thing is, if you do inverse function follows the original function, or function follows inverse function, basically the inverse function and the function undo each other. So if you do either one of these, you're going to get the original input back. Okay. Last thing is we're going to graph the original function, and we're going to graph the inverse function. So the original function we're going to graph in red. It's 2x plus 5. 2x plus 5 means the y-intercept is 5 and the slope is 2. 2, 2, 2. Okay. So that is the original function. And then we're going to graph the y equals x, which is the diagonal line that goes right down the middle here. And now we're going to graph the inverse function. 2, 2, 2. It's got a slope of 2. Okay. It's if you want to see the slope-intercept form equation for the blue line, it's y equals x minus 5 divided by 2, which means there is a slope of 1/2 and a y-intercept of -5/2. And we can see that the blue line indeed does cross, at -5/2, and it does indeed have a slope of rise 1 over run 2. Okay, so now let's go on to b, and we have this function here, which is y equals 3 minus 2x divided by 4. Let's use variable interchange and figure out what the inverse function would be. X equals 3 minus 2y divided by 4. Then we're going to multiply both sides by 4, and we get 4x equals 3 minus 2y. We subtract 3 from both sides, and we get 4x minus 3 equals -2y. Then we divide both sides by -2, and we get y equals -2x plus 3/2. So now we can graph this function and the original red function. The red function would be 3/4 minus 1/2 x. So the y-intercept is going to be 3/4, and the slope is -1/2 x, which would be a rise of -1 and a run of 2. So it would look kind of like that. And then the blue function is a y-intercept of 3/2 and a slope of -2. Y-intercept of 3/2 and a slope of -2. So the rise of -2 and a run of +1. Okay, kind of like that. And then if we were going to draw the line, the diagonal line, which is the y equals x reflection line, it kind of looks like that. Okay? All right. Number 3. Sketch y equals x, a dotted line, and the inverse solid line on the graphs on the same axis below. So we're just going to use the graphing. We're going to use the graphing method, and we're just going to reflect each one of these graphs over the line y equals x, which is this perfectly diagonal line here. Okay, and I'm going to draw the reflection in blue. So the easiest way to reflect these is to take the coordinates here, if they are marked, and this coordinate here is -2, 0, right? If we just invert the coordinates, the order of the coordinates, instead of -2, 0, if we put 0, -2, then that will invert this point here. Oops. So we'll invert that point to here, to 0, -2. And this point here, which is 0, 5, we invert to 5, 0. It's right there. Okay? So basically it looks like that. B. So in this one, we have a point here, which is 0, 4, and we invert that to 4, 0. And then the rest of it we just sketch it out like that. And then C, we got a point here, which is -3, 0. We're going to invert that to 0, -3. That's here. And the point 0, 1, we're going to invert to 1, 0, which is kind of right there. Maybe right there. Okay. And then D, we got this point here, which is 0, 1. We're going to invert that to 1, 0, and then the rest of it we just kind of sketch. Okay. And then, E, this is kind of a trick question. Do you see that if you reflect this line across the green line, basically you're going to get this exact same line, because this function is an auto-inverse function. It's its own inverse. And then this last one, you can see that the function is actually the y equals x line. The inverse of y equals x is also y equals x. So that just kind of ends up on top of itself, just like in E. So E and F are auto-inverse functions. 4. For the graph of y equals f of x given in 3a state the domain of f of x, the range of f of x, the domain of inverse f of x, and the range of inverse f of x. So we are looking at 3a, which is this function right here. Okay, and so first we're going to say, what is the domain of f of x? Well, the original function f of x basically ranges between x equals -2 and x equals 1, right? Including those 2 points. So I would say x ranges from -2 to 0, right? All right. What about the range of f of x? Well, the range of f of x looks like it ranges from 0 to 5, right? So it would be 0 to 5. Oops, y. Okay, and then C, the domain of inverse of f of x. Let's see. Inverse f of x is this blue function here, right? So what is the domain of that function? Well, looks like it is 0 to 2, right? So I'm going to put 0 to 2. And then the range of inverse of f of x would be, looks like 0 to -2. 0, oops, -2 to 0, right? Okay, and then if we look at what we put down here, look how -2, 0, it matches up with -2, 0. And on the other hand, 0 and 2 match up with 0. Oops, something's wrong. I did something wrong. The domain of the inverse f of x should be 0 to 5, right? Sorry about that. 0 to 5. And the reason why I knew I was wrong is because this is 0 to 5, and then the range of f of x should also be 0 to 5. So do you see how the range of f of x matches the domain of inverse f of x, and the domain of f of x matches the range of inverse f of x? So that's the relationship between the domain and the range. The domain of one is the range of other, and that kind of makes sense, right? Because we're inverting like all the x coordinates on the original function become the y coordinates on the inverse function, and vice versa. So it makes sense that the domains and the ranges get inverted, right?